This lesson is on proving a limit using the epsilon delta procedures. So let's talk about what they are. Let's talk about our definition and how it behaves and what it means. So we will start with our standard statement, which is the limit as x approaches c of f of x equals L. Which of course means as I get closer and closer to c from the left or the right, the values of the function get closer and closer to L. That's our informal idea. Well, now it's time to formalize that. So let's do it. What does that really mean? Given any epsilon greater than 0, there exists a delta greater than 0. You can find it. It depends on epsilon. Such that if zero is less than absolute x minus c is less than delta, then absolute f of x minus L is less than epsilon. Now, boy, this sure looks like a lot of alphabet soup, a lot of symbols on a page. Making sense of it is not easy. And the reality is, in the development of mathematics, it took a long time for the mathematical world to formalize this definition. So it's understandable that undergraduates would struggle with it a little bit. But I do think that it is a concept that you can begin to see at this level. Here is L. Here is C. As we approach C, the function values get closer and closer to L. So what does that mean? I choose any epsilon I want. I go a little bit above L and a little bit below L. A little bit above L, L plus epsilon, a little bit below L, L minus epsilon. And what that does is that creates a ribbon of values. And my goal is to choose x values close to c such that all of their function values are within that window. So I might choose c plus delta over here. So I choose a delta based on my epsilon. So I give you epsilon, you have to give me delta. And one of the big parts of this argument is going to be identifying what that delta is. So maybe f of c minus delta is here within the ribbon. Maybe f of c plus delta is here within the ribbon. C doesn't matter. Doesn't matter where C is. F of C could be anywhere, but all of the points near C have to be within that ribbon. We can't extend beyond it. That is in essence what this definition means. Now, how do we use it to prove it? Well, we start with that first line. We start with absolute f of x minus L less than epsilon being our analysis. And then we use that analysis to write our proof. So here's our goal. Our goal is to prove the following. Goal, prove the limit as x approaches 3 of 2x plus 1 equals 7. So just so we're clear on our notation here, our function that we're dealing with, f of x, is 2x plus 1. F of x is 2x plus 1. C that we're approaching, C is 3, and L is 7. Okay. How do I work through the process of building a proof? Again, I start with this part. I start with absolute f of x minus L is less than epsilon in something I call analysis. This is not the proof. This will give us the roadmap to build the proof. So I start with where I want to conclude. I want to conclude with absolute f of x minus L is less than epsilon. F of x is 2x plus 1 minus L minus 7 is less than epsilon. Plus 1 minus 7 minus 6. Absolute 2x minus 6 is less than epsilon. Factor out the 2. 2 times absolute x minus 3 is less than epsilon. Now I get absolute x minus 3 is less than epsilon over 2. And that completes my analysis. And now I'm ready to write the proof. Because that is the key idea right there. Proof. Given epsilon greater than 0, that is going to be the delta that I want. I'm going to choose delta less than what we have here, epsilon over 2. Okay. Choose delta to be epsilon over 2. Now, where does this start? We start with our if statement. Our if statement is 0 less x minus c less delta. So that's our if. So if 0 less than absolute x minus c, absolute x minus 3 is less than delta, which is in turn less than epsilon over 2. So that means absolute x minus 3 is less than epsilon over 2. And you'll see that I just work up the analysis backwards and I'll get to where I want it to be. So next line, 2 times absolute x minus 3 is less than epsilon. Beyond that, absolute 2x minus 6 is less than epsilon. This is the tricky part if you hadn't done the analysis, but it's trivial if you had done the analysis. So absolute 2x plus 1 minus 7 is less than epsilon. Which gives me what? Which gives me absolute f of x minus L is less than epsilon, and this completes the proof. That was our goal. Now, the reality is there's relatively few problems you can do this way. We're going to mostly focus on linear functions, and you may recognize a pattern here. But this is the process that I want to use to prove that a limit exists using the epsilon delta approach. Okay, let's do one more. Prove the limit as x goes to 2 of negative 3x plus 1 equals negative 3 times 2, negative 6 plus 1 is negative 5. So just so we're clear on our notation here, our f of x is negative 3x plus 1. Our c is 2, and our L is negative 5. We're going to start with analysis, and then we'll build our proof after we do the analysis. Our analysis always starts with what we want it to end with, which is f of x minus L less than epsilon. That's our final goal. That's how we start our analysis. Absolute f of x minus L is less than epsilon. Okay, what are we going to do? F of x, negative 3x plus 1 minus L minus negative 5 is less than epsilon, which will give me what? Absolute negative 3x. 1 minus negative 5 is 1 plus 5 plus 6 is less than epsilon. Factor out the negative 3, which is negative 3 times x minus 2 is less than epsilon? Well, what is that? The absolute value of -3 times the absolute value of x minus 2 is less than epsilon. The absolute value of -3 is just 3. 3 times the absolute value of x minus 2 is less than epsilon. And we complete our analysis by saying absolute x minus 2 is less than epsilon over 3. And then to do our proof, we just work the analysis backwards. So our delta is going to be less than epsilon over 3. So given epsilon greater than 0, here will be our proof. Given epsilon greater than 0, choose delta. This is x minus c. That's going to be the delta part. Choose delta less than epsilon over 3. Remember what this starts with. It starts with our if statement. It starts with if absolute x minus c is less than delta and greater than 0, but I'm going to choose to ignore that here. And then what? But what is c here? Our c is 2. So we're going to take if absolute x minus 2 is less than delta, which is in turn less than epsilon over 3, which gives me absolute x minus 2 is less than epsilon over 3. And then you can see we're just going to march up the analysis so that my next line is 3 times absolute x minus 2 is less than epsilon. But 3 is the same as the absolute value of -3 times x minus 2 is less than epsilon. Then I can put that -3 into -3 x minus 2 is less than epsilon, which is absolute -3x plus 6 is less than epsilon. And then we just keep going up, which is absolute -3x plus 1 minus -5. The negative signs here do make this more challenging, is less than epsilon. And then it takes me up to the top, which is absolute f of x minus L is less than epsilon, and this completes the proof. Now, again, there are very few functions that we can actually do this with. We've got to work pretty hard. Linear functions can always be done this way. A few quadratics can, some trig functions can. Otherwise, it requires much more serious mathematics to get there. But it's a nice idea. And again, you want to always go back to our basic definition. What does it mean? What is our limit definition, our epsilon delta definition? Given any epsilon greater than 0, we can find a delta greater than 0, such that if we're in that interval other than c, if 0 less absolute x minus c is less than delta, then the values of the function are close to L, which we write as absolute f of x minus L is less than epsilon.